So a very friendly welcome to Tom Papatheodore. Tom Papatheodore is an HPC engineer in the Systems Acceptance and User Environment Group at Oak Ridge Leadership Computing Facility, OLCF, at Oak Ridge National Laboratory. In this role, he develops and runs benchmarks applications to verify functionality and performance of OLCF's pre-production systems, work with OLCF staff and vendor partners to support early access users of these systems, and manages the pre-production training program for these users. He also runs regression tests and user-facing software for the facility's production supercomputers, organizes training events related to these systems, and manages the OLCF's involvement in an annual GPU hackathons alongside vendor partners and other partner organizations. And Tom is talking to us today about lessons learned from OLCF's Crusher Hackathons. Crusher is a test and development system for Frontier. And I will also say that Tom is also a Pawsey friend. He visited her some time ago, and I'm always, it's always great to catch up with you. And it's really great to have you here today. And good evening. So good evening, Tom. Thanks for joining us.
So thanks for the introduction, and thanks for the opportunity to speak here today at PCon 22. So as Machi said, my name is Tom Papatheodore. I'm an HPC engineer at the OLCF. So Crusher is our test and development system for Frontier. It's the system that the application teams who are preparing their codes for Frontier are currently running. And we've given some Crusher hackathons along the way. These teams have had access to the system since the beginning of the calendar year. And so along the way, we've tried to help them through our training program as well as some of these hackathons. And I just wanted to give some lessons learned from that to discuss some topics that could potentially be helpful for folks who will be using a similar system there with Setnix, and things that you might find useful or interesting. Okay, so before we get to that part, I just wanted to point out who we are in case there's folks who aren't familiar. So as the OLCF, we are one of the Department of Energy's Office of Science user facilities for computation. So us, along with the Argonne Leadership Computing Facility near Chicago, and NERSC out in California. And together we provide some of the world's most powerful computational tools for open science. Along with the ALCF, we are the two DOE leadership computing facilities. And so, we have this mission to provide these computational and data resources that are required for some of the most challenging problems today. There's always two centers, and we always have two separate architectures to address diverse computational needs. You get access to these systems through our highly competitive user allocation program, Insight and ALCC, where projects receive about 100 times more resources than at other centers. And I should point out that these are, these allocation programs, although highly competitive, are open to researchers around the world in any scientific domain. So this is just showing our progression from the petascale to the exascale. So Jaguar was our first petascale system back in 2009. It was a CPU-only system. In 2012, we moved to Titan, which was our first CPU-GPU system. Had a peak performance of 27 petaflops. And these were fairly simple nodes relative to today, right? There was a single CPU and a single GPU on each one of these nodes. As we moved to 2017, this is our current production supercomputer, which is Summit. It has a peak performance of 200 petaflops. Again, hybrid CPU, GPU, but in this case, it's more compute dense, the nodes. So you have 2 CPUs and 6 GPUs in each one of those nodes. And now we've reached the exascale with Frontier, and this is a 2 exaflop system peak performance. And again, it's CPU GPU hybrid. We'll look at that system here on the next slide. So Frontier, being our new supercomputer from HPE, it's powered by AMD. Both the CPUs and GPUs are AMD, similar to your system. It's a peak performance of 2 exaflops. That's double precision. There's 9,408 compute nodes that are packed into 74 compute racks, like you see here in the center of the screen. I'm going to get out a laser pointer here. Sorry. There we go. Right. The system has 29 megawatts of provisioned power. There's 9.2 petabytes of fast memory. So that's evenly split between the GPU's HBM and the CPU's DDR4. Those nodes are connected with Cray's Slingshot network. It has a Dragonfly topology. The node local storage, so that's 37 petabytes of SSDs. So there's SSDs on each one of the nodes. That's what that is. And although it's currently being stood up right now still, the system will eventually mount our center-wide Lustre file system that'll have a capacity of 716 petabytes. Right now, we're mounting the GPFS file system that Summit currently mounts as well. Looking at those racks, you can see here in the center. So these are large racks. These are 4 feet wide by 6 feet deep. There's 128 compute nodes in each one of these racks. They support up to 400 kilowatts of power. And they are heavy. They weigh about 8,000 pounds. So that's about the equivalent of 2 full-size pickup trucks packed into those cabinets. The nodes themselves, they consist of 1 AMD optimized 3rd gen EPYC CPU, 4 AMD MI250X accelerators. There's 512 gigabytes each of DDR4 and HBM. Coherent memory across the nodes. This is the 2 SSDs I mentioned. They're each 2 terabytes. The GPUs and CPUs are fully connected with AMD Infinity Fabric, as we'll see on the next slide. And there's 4 Cassini NICs for a total of 100 gigabytes per second of node injection bandwidth. This is an image of one of the compute blades. You can see there's 2 nodes on it. Actually, you might be able to see that. It's kind of small. But these pick up and they slide in vertically into this rack. And importantly, the entire system, the nodes are water cooled. So that includes not only the CPUs and GPUs, but the DIMMs and the NICs as well. So this is a diagram of a Frontier node. It's a lot to look at, but I will do my best to explain it. For those who aren't familiar already. So right, it's the same on Frontier as it is on Crusher. So you can see this, this large light blue rectangle here, that's the CPU. And you can see these dark blue rectangles. These represent the 64 physical CPU cores. They're labeled 0 through 63. In parentheses, you can see there's 2 hardware threads on each of these physical cores, and they're labeled as you see here. And these cores have access to 512 gigabytes of DDR4, which they can access at speeds of up to 205 gigabytes per second. These are the SSDs that I mentioned up here. Again, that's node local storage. Two of them, they're 2 terabytes each. Before discussing the GPUs, I wanted to just point something out here in our terminology down here in the key. So if you look at or are already familiar with the AMD MI250X docks from AMD, you'll know that they label those as MI250X GPUs, and that they have 2 GCDs on each GPU. And those are graphics compute dies. But if you query the system for the number of GPUs that are available, it's going to tell you 8 on this node, right? There's actually 4 MI250X, but there's 8 GCDs. And as a programmer, when you query the system, you'll see there are 8 GPUs available to you. And so we've decided to label these in our docs, which is where this image comes from, as GPUs instead of GCDs, just because it seemed less confusing, although maybe it's a little confusing either way. But right, so if I talk about GPUs moving forward, if I say GPU, I mean one of the GCDs for now on. If I talk about the MI250X as a whole, I will call it an MI250X. But just wanted to clarify that so I didn't confuse anybody who's already knowledgeable with the actual naming convention from AMD. Okay, so each of these GCDs or GPUs from this point on have a peak performance of 26 teraflops. They have 64 gigabytes of high bandwidth memory that they can access at speeds of up to 1.6 terabytes per second. I'm going to jump back up to the CPU for a minute just to point out that you can see you have these rows of physical CPU cores. So we have cores 0 through 7 that are all within this, share the same L3 cache. Cores 8 through 15 share this L3 cache, and so forth. These L3 cache regions, that's what I'm going to call them, although I believe AMD calls these core chiplet dies, or CCDs. These L3 cache regions, and so the CPUs within them, the cores within them, you can see are connected to a particular GPU. So this first set of cores, 0 through 7, are connected to GPU 4. Cores 8 through 15 are connected to GPU 5, and so forth. So this connection that you see here, this blue line, is the infinity fabric that connects the CPUs to the GPUs, and that has a bandwidth of 36 gigabytes per second, and that is in both directions simultaneously, right? So you can send data at speeds of up to 36 gigabytes per second in any one direction, but you can do that simultaneously. So if you want to consider that a 72 gigabyte per second bidirectional bandwidth, then I've seen people talk about it both ways. Right, and it's important, and I'll mention this in a couple slides, that you map from your correct L3 region to the GPU that's actually connected to it, right? Because there's more hops to get over to, say, GPU 0 down here to go through all these links, and then maybe out to the NIC or something. Okay. Right, and so you'll see that the GPUs themselves are all connected with these darker gray lines, and those represent the GPU to GPU infinity fabric. Those links are 50 gigabytes per second bandwidth each, again, both directions simultaneously. But you'll see that some of these GPUs are connected with one link, like 5 and 7, and so you can get up to 50 gigabytes per second bandwidth there. Some of them have two links between them, like GPUs 4 and 2, so that's 100 gigabytes per second for bandwidth. And then the two GPUs on a common MI250X have 4 of these links between them. And so that's 200 gigabytes per second between those GPUs. The NICs on the node are connected directly to the GPUs in this case. You can see that they're actually connected to a particular GPU, but whether or not you're sending data from one or the other GPU on the MI250X doesn't appear to give any performance difference. So that doesn't really make a difference. It's just the point that they are connected directly to the GPUs. And so using GPU-aware MPI is important in this case. So those NICs are 25 gigabytes per second each, as you see down here in the key. And so you end up with 100 gigabytes per second total bandwidth into and out of the node. The Frontier programming environment. So from the vendors, we have Cray's programming environment. So Cray, AMD, and GCC compilers. We have the Cray profiling and tuning and debugging tools, Cray's MPitch, which is optimized for AMD GPU Direct. Of course, we have AMD's ROCm programming environment that supports both HIP and GPU offload. Software from other sources, so we have things like Cocos, Raja, HPC Toolkit, for instance, through ECP. And then we even have a couple of things directly from OLCF, like we have some GCC enhancements so that OpenACC can be available on Frontier. Right, seems like I mentioned this already. Okay, well, I guess the Cray and AMD compilers are LLVM based, except for Cray Fortran. That is still CCE Fortran. So it's not LLVM based. And then we have GCC. So here you can see that C, C++, and Fortran are all supported by all compilers. OpenACC is most only supported by GCC, as I mentioned up here. OpenMP is supported by all compilers, but the there's variation on the level of completion that those have with OpenMP, their implementations. HIP is supported through both the Cray and AMD compilers. There's a semi-automatic translation from CUDA to HIP to the Hipify tools. CUDA Fortran is not supported on Frontier. Instead, we recommend that folks using CUDA Fortran on Summit, for instance, should instead write their any HIP portions of their code in C or C++ and have a interface from Fortran. Focus and Raja are available through all compilers, and UPC just from Cray and GCC. And the color coding here is just to show that these items in green are also available on Summit, with the idea being that we wanted to make sure that there was a porting path from Summit to Frontier for everyone, basically. So we have all these things available on the systems. Okay, so that brings us to Crusher. We've mentioned that it's the test and development system. It's 192 of these nodes that we just looked at. There's some documentation there that I'll refer to a couple times. The teams that have access to Crusher are the Frontier Center for Accelerated Application Readiness, or CAR teams. So this is 8 application teams. They each have a community code. And they have a range of scientific domains. Also, all of the application and software teams from the Exascale Computing Project have access to the system also. So there's a lot of users, I don't know, 1,100, 1,200 last time I checked, that have access to the system right now. Right, and so we work with the vendors to deliver documentation and training. We work with the vendors to hold Crusher office hours every Monday, so folks can sign up to come in and discuss any issues they're working on, profiling, whatever it is they want to work on. We've been holding these, and they've been helpful for teams. And of course, we are here to talk about the Crusher Hackathons, and so we also work with the vendors and ECP to deliver those. So right, finally, getting to the hackathons. These are 3-day events. They've all been virtual so far. And the idea is to help the CAR and ECP teams drive toward their development goals and whatever existing milestones they already have. We hold these with a combination of Zoom and Slack. So we use Zoom for the breakout room capabilities. They can move into their own breakout rooms to discuss their own application, share screens, that sort of thing. Use Slack for overall persistent communication. If you kill the Zoom session, of course, all of your chat goes away. And so, it's a good place for them to communicate. And really, they start communicating about 2 weeks before the event, then through the event, and then after the event through these Slack channels. And so it's just a good option to have for this persistent information. The original idea for these hackathons was, like I said, these teams got access to Crusher at the beginning of the year. And so we gave them a Crusher workshop, right, talking about the system, put together documentation for them, and just sort of let them go on the system. Where the idea was, it takes time for teams to bring their code onto the system, get any data they need, build dependencies for their code, all this stuff, right? And so we didn't want to hold a hackathon right away and, waste time isn't the right way to say it, but end up having them work on those sorts of things at the hackathon instead of getting the level of help that they can get directly from the vendors. And so we ended up, about a month after we gave them access, holding our first couple of Crusher hackathons. And it was a good idea, right, to do that, because we were able to let people work up to the point where they could no longer move forward, or maybe they were already running well, right? And only then do we bring them to the hackathon to start working on things and be able to take the most advantage of the OLCF, ECP staff, and the vendor staff for their projects. We've held 4 of these to date so far. They were super helpful in the beginning, and so we ended up holding 2 more in August and September here. And just to point out, in addition to the teams getting help with their applications, right, of course, is that, the teams learn how to use the vendor tools. They give feedback to the vendors on those tools and their software. They help identify new bugs, and this all, overall just helps to harden the software stack in the system. And so it's sort of a mutually beneficial arrangement. Okay, and so I have a couple of sections here. I have one on lessons learned, which are going to talk about some of the most commonly encountered issues that people ran into, and some of those, how to resolve them. And then I'll have just some tips afterward that people came up with along the way. So what we saw in most cases is that when people ported their codes from Summit to Crusher, they found that that initial port was pretty straightforward, right? So this was actually something that some of the teams were concerned about, right? Okay, we're using CUDA, we're going to move to HIP, supposed to be able to translate this, let's see how well it works. And it did work well. But that there was certainly optimizations that were needed to realize expected performance. And so what we found is that a lot of application teams found similar issues that they needed to figure out, right? First, a lot of teams didn't necessarily understand how to decide what the expected performance for them was, and so we had to address that. And there's of course the usual suspects, so occupancy, register pressure, kernel, launch parameters. But then there were some system-specific things that I'm going to mention on the next couple slides, like Slurm bindings, GPU hardware atomics, and managed memory. And it turns out that when the teams addressed, whatever subset of these issues were relevant to their application, that they were able to find this expected performance. And so we did have good success, figuring these things out during these hackathons. So some of the teams, when they first started, they see, from the documents that, a V100 from NVIDIA is about 7.8 teraflops. One of the GCDs or GPUs from MI250X is about 26 teraflops, so my application should be about 3 times faster. And it's not, and what's going on here? And that's just not true, right? It really depends on your application. The expected performance when moving from one system to another is completely dependent on your application itself. And that's something that, in hindsight, is obvious, but if they're just trying to understand in general, that's what some teams did. And so we ended up giving them this way of trying to figure out what performance they should expect. So we start off by asking, is your application GPU bound or are you data transfer bound? If you're GPU bound, are you compute bound or memory bound? So if you're compute bound, well, then maybe you can look at this first row here, right, to see that maybe you should be around 3 times faster. That's, of course, probably only going to be true for a particular kernel, unless that kernel just completely dominates your entire runtime. But that's a way to look at it, right? If you're memory bound, you'd probably want to look more at the HBM rows here, right? So the bandwidth to the HBM on one GCD is about 2 times faster than it is on a V100. And so, if you're memory bound in the GPU, then maybe you're expecting about 2 times faster instead. And you shouldn't expect that full 3. And this is just a GPU to GCD comparison, by the way. I do have the node level comparisons over here too. But when folks started out, right, they would just try to do a single GPU run for their sort of ha-ha tests at the beginning. Right, and so of course you need to profile your code to make sure you understand where the where you are dominated, whether you are compute bound, memory bound, these sorts of things. But this was generally what we tried to show them, right? It's not going to give you an exact number, but it is a way to understand for your application after profiling it and seeing the different components, what you should be expecting. And so this ended up being very helpful in hindsight. I guess it's obvious, but it did turn out to be helpful for the teams. Okay, so now that the teams understood what their expected performance should be for their application, if they still weren't seeing the performance that they expect, then we had to start looking into other things. One of the first things we did, which was also important on Summit, was to look at the GPU bindings, right? These are no longer simple, Titan style nodes where you have a single CPU and a GPU. There's mapping of all of these GPUs that you need to do, and that can be unintuitive. So remember what I said, that you need to, if you have a MPI rank that lands, say, in this L3 cache region, then that MPI rank is going to want to target GPU 4. And so we need to make sure that this type of a mapping is happening. And so we ended up making this application. It's really just a Hello World program called Hello Job Step that's available on GitHub that writes out useful information. It tells you which physical cores or hardware threads your processes, so your MPI ranks, and your threads landed on, and it tells you which GPUs you have available to you. And with the GPUs, it can tell you different GPU IDs that I wanted to point out before moving on to the next slide so that you know what they mean. So GPU ID, this is what you think it means. It's the GPU ID that you see here on the node, right? It's sort of the global node level GPU ID. The runtime GPU ID is what the HIP runtime sees as your ranks. If you only give one GPU to each MPI rank, the runtime is going to label that as 0. That's the way it works here. That's the way it works on NVIDIA systems. It's just the difference between the two IDs. Hopefully that'll become clear when I show you an actual example. And then I've included the bus ID in this program because sometimes those GPU IDs can be confusing, and you want to make sure, I want to know for sure that I'm running on a separate GPU. And so you can look at the bus ID for those GPUs to show that it's in fact unique. Okay. So here's an example of what someone might do, and some people did when they first got on the system. For this Hello Job Step program, I have just set OpenMP num threads to 1 because for simplicity. So you have this job step, and folks were running, srun -n capital N1, and that's one node, 8 MPI ranks, 8 CPU cores per rank, and 1 GPU per task. That seems very fair. If they looked in, say, the srun man page, that's what it might tell them to do, and then they run, right? And then we sort this to make it easier to look at. And what you can see happens is that MPI rank 0 landed on hardware thread 7, which is here. So it is in the first L3 cache region, and so should be mapped to GPU 4, but it's not. The node level GPU that it's looking at is GPU 0, which is down here, and not ideal mapping. Now, there is a simple solution to this, and that's just to add in this -- GPU bind equals closest, and after some bugs submitted to Slurm, it does give you the correct output now. And so that's an easy way to boost your performance on the system that is, again, obvious in hindsight, but not everybody necessarily reads over the documentation as best as they can. We had examples of this in our documentation, our quick start guide, but some people look directly at the srun man page, right, which is fair. And so, it was important that we, in subsequent trainings, that we did point this stuff out to them so that it's not just the folks at the hackathon that realize this, but everybody on the system. This is something else that can happen that we saw happen. Back here, we had GPUs per task equals 1, but some folks would see GPUs per node, and they would set it equal to 8. And what you can see happens here, where this job step is identical except this one flag, each MPI rank has access to all GPUs, right, that you see here. And so what happens is, unless you have logic in your application itself to programmatically map the MPI ranks to GPUs, then everybody's just going to target the default GPU, which is 0. And so all these ranks on the node are going to all be running on GPU 0. And of course, that's not going to give you the performance you expect because you're leaving 7 GPUs on the table. And this is something that, again, can just be resolved with this GPU bind closest anymore. But at first, that didn't work as expected. And again, isn't necessarily obvious if you're just looking at the srun pages. So easy solutions, of course, which is great, but it does really make a difference in your performance. And it's something that I think should just be common practice on these fat nodes anymore. Okay. We understand what performance we should expect now for our application. We've made sure that our bindings are correct. I'm still not getting the performance that I expect, right? I'm not getting that 2 times or whatever I think I should get. What is going on? And so this is where, teams started actually profiling their codes at the events. And several of the teams ended up narrowing it down to where it was the GPU atomics that seemed to be causing the issue. Well, fortunately, AMD realized right away what was going on, and that's that unless you specify by using this -m unsafe FP atomics flag, your GPU atomics are going to be performed in software instead of in hardware, and that can make a very big difference in performance. So you could see the name of that flag might raise your eyebrow, right? To think, okay, it says it's unsafe. I don't know if I should set this. And so it turns out that whether or not it's safe to use that depends on the granularity of the memory that you've allocated, where granularity here refers to the coherency between the memory being used inside a kernel and the memory in the rest of the system. So there's coarse and fine-grained memory. If you have coarse-grained memory, then coherence with the rest of the system is obtained like you'd think it would be, right? At synchronization points. HIP device synchronize, the implicit synchronize inside of a HIP mem copy. But fine-grained memory is also available, and it allows the CPU and the GPU to synchronize while the GPU kernel is still running. And so, importantly, you can only use this flag. You can only use the hardware atomics, and so should only use this flag with coarse-grained memory. And if you use it on fine-grained memory, it's going to silently produce a no-op, which means it's not going to do anything, and so that's going to give you incorrect results, which is a whole different problem. And so this is something that needed to be sort of documented for our users so that they weren't running into this issue, of course. But it was something that we learned by several teams hitting it at the hackathons at the beginning. And so if you want to know which memory allocators allocate coarse-grained versus fine-grained memory, you can look at this section of the docs that we have that AMD actually added right into our quick start guide. One of the benefits of us moving to open source documentation is that we can just ask the vendors to add this in there for us. So we're very grateful. They've been great doing these sorts of things. Okay, another issue that people encountered. Some folks were using managed memory, and so managed memory just being right. Well, typically on NVIDIA GPUs, right? CUDA malloc managed, that sort of thing. HIP malloc managed on these systems, but they were seeing some pretty poor performance. And I agree. When I looked at it, it was not good performance, and it did seem to be related to the managed memory because they had 2 different versions of their code, one of the teams anyways, and when they had the explicit memory, it was fast, and when they had the managed memory, it was poor performance. And the reason is that managed memory on these GPUs can be enabled either using zero memory or zero copy memory access or page migration. And unless you understand about XNAC and how to enable XNAC, the users really didn't know which one they were getting. So you don't really need to understand XNAC. You just need to understand what it is. XNAC is the functionality on these AMD GPUs that allows them to migrate pages on page fault between the CPU and the GPU. So that's something that isn't enabled by default, and so they were getting poor performance. It's something that needs to be enabled both at compile time and at runtime. So a code that is enabled at both compile and runtime. So you enable at runtime with this environment variable. Then you will get those migration of pages between the CPU and GPU on page fault. If you don't enable those at compile and runtime, then you're going to do zero copy memory access. And if you're not familiar, what that means is that the GPU is going to directly read from CPU memory across that Infinity Fabric link instead of transferring the data. or vice versa, right? The CPU reads directly from GPU memory. Right, and so that's can actually give you quite a slowdown in some circumstances. So on Crusher, and I believe this is a system-specific configuration that you can set. We by default compile in what's called exnac any mode, right? So there's exnac on and off, and then there's exnac any. And that's just for the compilation phase. And what that says is, if you do exnac any, it means that you compile for both with and without exnac support. So that means you can just flip the switch on this environment variable to give you either, to either enable it or don't. And you don't really need to worry about it at compile time. But that depends on how you set up your system. There's more information down here about enabling GPU page migration in our quick start guide if you're interested in more information on that. So another area that people were seeing issues with that wasn't specific to something like GPU atomics or managed memory, but was just sort of found across all applications, well, not all of them, but across applications generally, was issues with register pressure. So the GPU registers, it's a scarce resource, and it's one of the things that determines occupancy, right? Occupancy isn't only the cores on the GPU, it's other things as well, right? Like things like registers and having those be available. And so if you're really, pounding those registers, you can have spillage, and it can really slow down your application. And we found that turned out to be the case in several app teams' codes, and so it was something that needed to be looked into. And it was found at the hackathons, and so fortunately we had vendor support there to sort of grasp what was going on. And so what you could do is you can look at the ISA, or the assembly code that's generated when you use this --save--temps flag, and that'll give you information on your register usage. And so it was something where they were helping individual teams with it every time. And so we ended up holding a special session on it where we have the slides and the recording of that session here, if you care to look at it, to give sort of more general audience access to this, because it's something that needed to be done. And so this shows you how to use the save temps flag to generate this information, and it also shows you some techniques on how you can reduce that register pressure to improve your performance. GPU profiling, this is something that's, like I said, useful sort of at all stages of your development. We have some docs showing you how to use RockProf to manually create like roofline plot. But AMD's MIPerf and Omnitrace have ways of doing this automatically. And so it's much simpler to use. Unfortunately, MIPerf is still to be determined on its release date at the moment. And for anybody who's not familiar, Omnitrace is similar to NVIDIA's Nsight Systems, where it shows you sort of a big picture view of your code so you can identify hotspots. And then MIPerf is similar to NVIDIA's Nsight Compute, that lets you sort of dig into the kernel itself to see what's actually going on once you've identified it as a hotspot. And the last of my lessons learned here that I want to point out is the L1 cache. So we had a couple of teams who were L1 cache dependent, right? They were very sensitive to this L1 cache. And so the L1 cache is about 6 times smaller on one GCD of an MI250X than it is on the V100s. And so this team that had really tuned their code for the L1 cache on the NVIDIA V100s did run into an actual hardware limitation here. And so they're currently working with the vendors to try to see if there's anything they can do, right? So it's a hardware limitation, but maybe there's something clever they can do when it comes to shared memory or whatnot to try to resolve this. So that's something that you might want to be aware of too in your porting efforts. Okay. I'm going to move on to talk about some helpful tips now. These are slightly lighter subjects, if that was a lot to consider all in that quick go. So there's things like Slurm tips, right? There's people who are trying to debug their applications with print statements. That's fine. And they weren't getting any output. So if the code was hanging or it was crashing and they weren't getting output from their print statements, of course, that's not helpful. The -u flag, oh, and the reason was because by default on the system, the standard out was being buffered. And so you wait until it fills up a buffer before you dump it out to standard out. And so we were able to give this -u flag, which gives unbuffered output. And then, they were able to actually get some useful information out while debugging with these print statements. And so that's something that's a simple tip, but of course, something that some people didn't realize at first, asked questions about it. So it seemed like something relevant to add in here. The -l flag prepends the task ID to lines of standard out. That's helpful. I'll actually show you an example of that in just a minute of where I've used it. Sometimes you run this S account, you try to look at jobs that have run maybe a couple days ago and you can't seem to find them. You can give a start and end time for S account so that you can find jobs that are maybe not visible by default anymore. So I think, again, that's something that's maybe configurable, but something that we needed to do. This is actually something that I took directly from the Pawsey SC docs. Whoever wrote that, I appreciate it. I've adopted it and now give this advice to our users. So it's to capture job information inside of your batch script, right? So you can add this S-control line here, and it'll dump all this information out in your standard out file. Then you have your application output, and if you put this at the bottom, it gives you, like a quick and dirty elapsed time. And you can even have it print out some other information if you wanted to. And just having that all the time in your scripts, that's great. As well as I would also add module list in there just to show what modules are loaded for you and for any support tickets you submit. This -t, by the way, if you're not familiar, this says give terse list. So it doesn't give you that sort of spaced out view of all of your modules that you try to drop into an email and it's hard to look at. It gives you just a list of your modules. And so it's something that's helpful. And, where this can actually be helpful is sometimes there have been a couple occasions where a user has submitted a ticket and said, my code crashed. Okay, well, that's not super helpful. So it's a very extreme example, but I guess I'm pointing out here that when you're running on these systems, especially when they're pre-production, right, or they're these new systems, you're going to encounter issues. And, having as much information as you can on that to give to the folks that you submit tickets to, either at OLCF or at Pawsey, that's really what we need. It's super helpful. We're probably even going to ask you for that information. You'll have to go back and get it. And so, having this information about, the node that you ran on, the job ID, so we can dig into it deeper, the module list that you had when you ran your program, this sort of stuff, is very helpful. And if you can just automatically add it into your scripts, that's a great tip that I've picked up for Pawsey, and I appreciate it. So I'm passing it on to other folks. This is another way you can test your Slurm bindings if you don't want to use that hello job step program. It's sort of a quick, dirty way to do it. You can see what's in red there. That's the actual bash command that you're running. And it shows you similar output. You can see that I've used that -l flag here to prepend the MPI rank to the beginning. That's great because it tells you which MPI rank, and it lets me sort these by MPI rank too, since it puts it at the beginning. But right, you can see the MPI rank 0 ran or has access to cores 0 through 7 and has access to GPU 4 and so forth, which is the correct binding. This is slightly different from that Hello Job Step program, though, in that it shows you which cores and GPU your MPI rank will have access to if you actually run something. The Hello Job Step program tells you where it actually ran. It reports from the core that it actually ran on. And to me, I like that level of, matter-of-factness, I guess. So that's why I prefer the other program, but this is a quick and dirty way to do it if you want. For both of those, unfortunately, you do need to actually have an allocation, so an interactive job or a batch script or something. Debugging issues on a compute node. So this is something a lot of teams actually found useful. So you're able to grab one node in an interactive job, compile your code, run the code, and let it churn. And then in another terminal, you can look for your node that you have access to. I can see here from SQ that my job is running on Crusher 001. I SSH directly to that node. I can run hostname on it, make sure that I'm actually on that node. And then you can do things like ROCm SMI. You can see the process IDs. You can see the memory use to see, am I actually lighting up the GPUs that I think I am, or any GPUs for that matter. Or you can do things like, use PS or top to get your process IDs, and then connect to the running processes with like GDB or, rock GDB or something. And it gives you a lot of helpful information. This isn't something that's necessary, but for folks that are so inclined to do their own debugging in this way, it can actually be very helpful. And again, helpful to be able to give to the support folks when you submit tickets. So this is something that we recommend our users do, and just tips and stuff, right? RockProf tips. So these are other things that we found that people found useful or that they even reported. So this isn't telling you how to use RockProf. It's just showing you, if you compile your code and you run it on on the node, okay, well, you've compiled it, it ran, it gave you a time reporting, right? Did it actually run on the GPU? If you want to know the answer to that, you can simply add this right here, this rockprof -- stats, and it'll print out a file that tells you, some stats about the kernel that was run, which in turn shows you that it did indeed run a kernel. So sort of a quick, dirty way to make sure you ran on the GPU. If you are running an MPI program, and say you're running on a single node, but you're running 8 MPI ranks, and each has its own GPU, you might want an output from each of those MPI ranks. If you don't do that, it's going to be super garbled, right, in your standard out. And so what you can do is you can make a wrapper script like you see here, and it has this rockprof, stats, hip trace. This is the output file, and you can give it the slurm MPI rank ID. And then it will print out one output file per MPI rank. And so that can be helpful. You just run it right before your executable like you see here. Oh, I should also point out, this rockprof stats needs to be before your executable, but after your srun command. We've certainly seen folks who have put rockprof before the srun, and that profiles the srun itself instead of the actual application. So that's something to make sure it's in the right order. Right, and let's say that you're running on multiple nodes, you have 128 MPI ranks, and you just don't want to look at 128 ranks worth of individual files. If you have, this is particularly useful if you have an application that is essentially doing the same thing on each rank, right, and is load balanced fairly well. You can write a script like this, and it will basically grab, if I'm MPI rank 0 or whatever you want to put in there, just give me an output for, just profile that one rank, and then it'll show you the output for just that rank. And it's a way to make that easier to look at. There is a way, I think, to be able to write multiple MPI ranks to the same file and have it in a coherent way that I've seen, but I'm not able to. I wasn't able to pull that out for these slides, unfortunately. So know that that's possible, and you might want to ask somebody at AMD about that. This is another way to check if your GPU is being used. It only works for Cray's OpenMP offload, but you can just add this flag in here. Cray ACC debug 1, and it'll show you things as you run, like, ACC transferred 3 items, executed a kernel, transferred 3 more items, and it shows you, you did run on the GPU. Okay. Just finishing up here with some final thoughts. There were some teams, application teams, who were sort of, bouncing the idea back. Do I, attend one of these hackathons, or do I just continue doing these things myself? It's 3 days of time that I'm going to have to set aside for this. and I'm going to get on a soapbox real quick and give my answer that I gave to them. So all of these teams are already working on something, right? It doesn't matter what it is. They're trying to achieve their expected performance. They're scaling up, profiling their code, whatever they're doing. They're working on something. So, they could work through this on their own like they do in their day-to-day work, right? And what might this look like? So you might be working on an issue that you've run into, whether it's trying to compile your code or a runtime issue or whatever, and you're trying to figure it out, trying to debug it. You don't have much luck one day. You have a meeting you need to go to, so you go and you do it. You come back to it the next day, still no luck, and you decide, okay, I'm going to bring this up at the group meeting at the end of the week with the other folks who are familiar with this code. You decide during that meeting, okay, this is something that we do need help with. I don't really know how to address this myself, so let's submit a support ticket. Your support ticket comes in, someone takes it from OLCF or Pawsey. They can get it or they don't, or they can answer it right away or they can't. If they need to, they can send it off to the vendors, and this can be a week-long process to sort of figure out a particular issue, right? That's not uncommon. Or they can come to one of these hackathons and they can sort of short circuit that loop there, right, of getting that feedback. And they can ask questions directly as they encounter them to OLCF or the vendor staff. And so this sort of thing is what the participants came back with when we asked about, the benefits of this, and said, really, this has taken 2 weeks worth of work and accelerated it, crushed it down into 3 days. And that's great, right? They were super happy with that. And that's the point that I would try to make to these folks is, if these sorts of things are offered, sort of like the sprints that were mentioned earlier that will be in the next talk, that's something that if you can take advantage of it, you certainly should. That setting aside that time is the benefit of it, right? Some people would look at it like a burden, but in fact, that is the benefit of it because of how much you can get accomplished in those days. Anyways, okay, I'm off my soapbox. I'm back to talk about the additional benefits, and these are mostly for the center, right? These are the benefits that we found in addition to what we found for the teams themselves. So we can collect these lessons learned and give these sorts of talks, right? We can inform topics on special sessions, like I mentioned that we did for the register pressure. We can create additional docs that I've showed you along the way. We can share information with other centers with similar architecture, which we're always happy to do. You get this large push from all these application and software teams that are really stressing the system, and it helps to identify, software, compiler, hardware bugs, beneficial to everyone around. And specifically for us at OLCF, we found great interactions between our ECP software technology teams and the ECP application development teams. So what I mean by that, the software technology teams are the folks like the HPC toolkit team. So they come in and they help teams learn how to use their tools. They profile their codes for them. The OpenMP folks through the Solve project are there to help the OpenMP teams. The Cocos folks are there to help the teams using Cocos and so forth, right? So it gave this great integration of the ST teams with the AD teams. And so super helpful in that aspect too. So another benefit that we found out of these. These are just some helpful resources. I've already pointed to the quick start guide a handful of times. What I didn't point to is the known issues. So we actually have this set up to where we use Jira for our tickets, and we use Jira to automatically populate this section of known issues so that when we don't ever delete them, but we move them, based on the status in Jira, we can say whether or not it's a open issue, it's an issue with a workaround, or it's a resolved issue. And so the point being there is that this is always up to date. And so if anybody from Pawsey ever wanted to look here for issues, you could do that. Right, software compatibility. This is someone from the group that I'm in, the System Acceptance and User Environment group, that has this script that he runs that makes this chart of compatibility between Cray-M, Pitch, and ROCm. It's not super robust, but it's actually running a test on the system to test basic compatibility between them. And so that's something that's in the docs that we always have updated. Profiling applications, I guess I don't need to cover. This is super useful, and I would recommend to anybody running on one of these systems that needs to port their code from CUDA to HIP to bookmark this page. It's actually kind of hard to find because it's in the Hipify GitHub, but it links to other links, and the links go to the HIP runtime and different HIP libraries. And what it is, it's a compatibility chart that shows you in CUDA, this is the call, in HIP, this is the call. And so, most of the time you run your Hipify tool and it translates things for you. But it may be that once in a while you run into something that it doesn't recognize. And it could be that it's a slightly different notation than just the, CUDA being changed to HIP, or, something like that. Or it might not be available until ROCm 4 or 5.4, for instance, right? And this shows you that sort of thing, right? Yes, it's available, but it's not available till ROCm 5.4. So super helpful when you're doing your porting. I didn't know about it till about halfway through some of our porting efforts, but it is there and it's great. Training archive, we record all of our previous trainings if you ever want to look at those. This was something I found during the first hackathon, which I was surprised to see. Man intro _ I knew about MPI, for instance, and OpenMP, but I hit tab a couple times and realized how many of these there were, and have found these to be useful along the way too. They're, documentation, just like man pages about some of these topics. So super helpful. All right. In summary, it was important for us to show the application teams that the performance that they should expect is application specific, and how to, figure out what this performance should be. There will likely be optimizations needed to expect or to realize that expected performance. The good news is in that case that a lot of those things are these simple fixes that I mentioned, right? Things that just aren't obvious at first. But with people sharing lessons learned like this, like we do with the rest of our Crusher users, they're now able to take advantage of these from the start, sort of start ahead of the curve. And hopefully that helps some folks at Pawsey as well. Right, profiling your application is important. I've said that about 6 times, so I don't need to go into detail there. Might need to look at the GPU register usage if you're still seeing unoptimal performance after taking into consideration some of these other things. And of course, this is something that we have access to that most other people in the world don't, right? Folks at Pawsey and folks at OLCF, folks at Lumi, or with the Lumi supercomputer, I guess. And sometimes we get bogged down with debugging, right? You're scratching your head, staring at a code instead of thinking about how awesome it is that we're running on some of the most advanced supercomputing hardware in the world. So I always tell our users to make sure they're having fun along the way. Okay, and with that, I will take questions if there's any time, or if anybody has any.
Yeah, we have a lot of. So first of all, Tom, thank you so much for the talk. It's been awesome. I think I will start with a short question. We will be able to share the slides as well, because there were a lot of detailed things and instructions that I saw a lot of people were making notes. It would be really good to have a copy as well to share it over our Slack channel.
Yeah, absolutely.
Cool.
Yep.
And now
I'll join that Slack if you want, and I can drop a PDF those slides in there when I'm done.
So now the questions.
Okay.
Hi, thanks for the nice talk. I've got a double barrel, maybe triple barrel question. So people are sort of have been starting essentially from CUDA and then porting to HIP, just because, the NVIDIA systems have been around for a long time. So through this porting process, have you found that there's been a feedback loop and that people's CUDA codes have improved? Are they working with divergent source trees? And so the final relation is there used to be this language, well, maybe there still is a language called Ada, and there was some very specific sort of things in that you could use to program kind of sort of generic task-based programming. It had its own sort of implementation of a threading model, and so can you envisage a future where maybe sort of in Fortran and C that there's just extensions to the language where we can just write directly a portable code without having to worry about sort of this switching back process?
So answering the last question first, that is already available. Well, for a particular GPU vendor anyways, right? It works well right now. So NVIDIA has been giving talks on this for quite a while, right? About using standard language to do this, whether it's C++ or Fortran. I know there's some GCT talks from recently, GTC, where they've done just that. It's just extensions to the programming languages themselves, and so it takes a while to get in there because the standard moves fairly slowly relative to something that's lighter weight, like OpenACC or something like that. So in answer to your other question, you asked about the feedback, right? That has certainly happened. One of the things that we tell people, so not everybody has access to this system, right? Not all of our users. We have our main allocation programs, our Insight and ALCC, and these folks don't yet, most of them anyways, don't have access to this system. And so they're on Summit, and that's what we've said all along. Where you should be, the best place for you to be working on your code and preparing for Summit or for Frontier is on Summit. We have the same programming models. We've added HIP there. And so they are continuing to improve their codes there. So we have these GPU hackathons that we do every year with NVIDIA, and they're continuing to work there. And any improvements they make there helps their HIP codes. One more thing I wanted to say. Sort of related to your questions. There were some teams who were just unwilling to move their CUDA codes to HIP. And what they did was very clever, and I love this idea. You might have already heard of this, but there's a code called Choya, which is an astrophysics code. And what they did is they left everything in CUDA and simply put a header file that does the translation for them. So it has a bunch of macros, defines where it says CUDA memcopy is now HIP memcopy, and it works for most of these things. There's some things you'll encounter where you need to make changes, same way that you would need to make changes if you actually HIPified it. But it was a pretty clever idea. And in fact, I used that recently. I was at a Tapia conference, and I wanted to give a GPU tutorial on our AMD system, Spock, which is actually now my 100 system, but I feared that some people wouldn't come to the talk because it was going to be on HIP, and they might not know what that is yet. It will be eventually, but it's limited, right, in what it is at the moment, or at least in the the systems that people are using it on and that sort of thing. So I used that same method, and I taught them CUDA on the AMD system. It felt strange, but it worked very well. So seems like there was one more question I might have missed there. If I didn't answer all your questions, feel free to ask the other one.
I have questions as well.
Sure. Yeah.
Hi, Tom. Thanks for the talk. It was very nice. My name is Christian. I work at Pawsey, and I've been playing also with ROCm and MI100s. I've seen two questions mainly. I'm very curious about the unsafe atomics and in which cases we can actually use it. And I was wondering if you could show some practical examples, because I'm using atomics while the kernel is running is the main reason to have atomics, I guess. If you have to synchronize first, probably use some of that advantage. So that is one question.
So I may have confused that. It's not that you need to do any sort of synchronization or anything like that in order to use it. It's that I was trying to explain the difference in the coarse and fine-grained memory. So that just the difference in what coarse and fine-grained memory is where I was talking about those synchronization points. If you have coarse-grained memory, you can use that flag for hardware atomics. Now, whether or not you're using coarse or fine-grained memory is something that you can look directly at those docs, and it shows all the allocators, right? It shows HIP malloc, it shows HIP malloc managed, it shows just malloc, right? Because malloc can be used in this unified environment. And it's all there in the documentation. I don't actually have them in my head to know which ones it is. But you don't really need examples. It's just more of what are you doing in your code to know if you can use that.
Okay.
Does that make sense?
Yep. And the second question was about more on the CPU side. I've written a small code, K-means implementation, very simple. I've been trying to test the scaling on a single CPU with from 1 to 128 cores. And I've seen very poor scaling, while on the previous system we had system from 8 years ago, I can see a perfect linear scaling. Whereas if I go beyond 8 cores on AMD CPUs, I see a sharp drop in the scaling in the code, essentially. And I was wondering whether that can be due to the new L3 cache system. And I was wondering if you observed the same.
So I haven't observed that personally. I would have to look at the actual CPU diagram. I know there's one on the Pawsey site. The reason that I haven't seen it yet is because we don't have any CPU-only nodes, and so most people aren't using just the CPU in that way, right? They're using the one rank per 8 cores basically, and then using OpenMP threads just on the 8 cores in that particular cache region, the L3 cache region. So I guess I don't know. That's something that we should certainly investigate. I apologize that I don't have an answer for that, but I think just because everybody's so focused on the GPU, since it's like probably 99% of our compute power, that's not something we've run into. But I'm going to write that down and check on it myself. Sorry, that turned out to be more of a question that helped me than you, but I don't have an answer for it. I'm sorry.
No worries. Thanks. Thank you very much.
We have at least one question in the room still, but we also have one question online, and that's from Ash. Ash, if you like to unmute yourself and ask the question.
I think he wants us to ask.
Yeah. Just give me a second.
Yeah.
I can look in the chat if you want to.
So Ash's question is, were there any issues when moving from latest CUDA versions of code to HIP-based?
Not. The answer is no to your very specific question of from the latest CUDA to the latest HIP base. Now, whether or not you're actually using any of the features, the latest features, that's a different story. Right, HIP is behind CUDA. CUDA is more mature. HIP is sort of trying to catch up in that sense, and so it's always lagging a bit behind. And so there are always going to be features that aren't going to be available. If you're using the latest and greatest features on the NVIDIA GPUs, then it may be that you're going to need to wait for subsequent HIP or ROCm versions to be able to see that. But we have seen along the way that those things, at first I think the idea was that it was essentially up to CUDA 8 where HIP was, right? And now it's much further than that. And so along the way we have seen them tracking what's this functionality that people want from CUDA in HIP, but it does lag behind. So if you're using the latest and greatest features, then yes, there could be situations where people are going to run into functionality that's not there. But again, look in that that compatibility guide that I pointed to in the last slides, which I'll post in a minute, and it'll show you, right, if it is something that's just not there until ROCm 5.4, it'll show it there.
Hello, Tom. Thank you very much for your talk. It was great. And my question is about getting a roofline plot. using RockProf that you said some of the teams managed to do that. And is there any issues arise while doing that for the teams that you could share with us? I'm also curious about what kind of flags of RockProf they used, and yeah.
Yeah, just to add to Oscar, we had instruction lines and group lines. So instruction intensity versus floating point intensity, but that's harder to interpret. So we were kind of stuck at trying to do a proper roofline model with RockProf statistics.
So do you know which version it was of RockProf or which version of Rockham it was?
So we were primarily using 4.5 because that's what we had on our system. I've been trying 5.0.2, but I haven't gone back to try to make a roofline model with 5.0.2. I haven't tried fully 5.2 yet to see what it provides.
I think you're going to need those later Rockhams, Rockham 5.1, Rockham 5.2. There were some metrics that just weren't available. They were there, but they weren't made accessible yet in those earlier Rockhams. And so they are now, and so you should be able to do it. And in fact, in our docs, and I point to it, a link to that specific section in the slides there, one of my colleagues in the group that I'm in wrote a section on how to do that with RockProf. So you should be able to follow along with that, but you will need to use the later Rockhams.
Okay, thank you. I think we can still have one more question from the room, if there is anyone. If not, actually, I'm keen to ask one question. So
Sure.
with the amount of memory you have on the GPU, I guess a lot of teams might be looking at moving most of the code on the GPU and then use some kind of a communication which does not involve, so there's kind of a RDMA or zero copy communication between the GPUs. So did you have any experience with that and any lessons learned related to how to set that up on Crusher and Frontier?
I mean, I think that sort of thing is really application specific, right? On whether or not you can make your data live on the GPU longer, right? Or permanently if you can. We certainly have teams that are doing that, and that's what we encourage teams to do, especially since the NICs are connected directly to the GPUs, so that you don't have that additional transfer that you would have if you're sending directly from the CPU that you wouldn't have on other systems. So lessons learned, I don't really have lessons learned on that, but I would say that on these systems with these NICs connected directly to the GPUs, it's even more important to do that. And of course, like you saw in the table that I had on expected performance, that bandwidth between CPU and GPU is actually lower on Frontier than it was on Summit, which again makes it more important that things need to live on the GPUs in these systems.
Okay.
Things being data.
Thanks, Tom, and thank you for spending your evening with us. So I'll ask all the attendees to thank Tom again.
Hey, I am happy to help. I'm certainly a friend of Pawsey, and I look forward to collaborating further in the future. Thanks for inviting me, my friend.
Thank you, Tom.